This is going to be our last video for Unit 3. This is Unit 3, Day 11. So we've gone through now solving quadratic equations by factoring. Yesterday we solved by graphing. There's one way we haven't gone over that's actually one of the most important ways for solving a quadratic equation because it works for anyone. That's the quadratic formula. So the reason we have this formula, I'll put it up here in a second, but you're going to see it's very complicated. So we can't solve all quadratic equations by factoring or by graphing. Right? There's some that don't factor. There's some that are not going to have x-intercepts. So when that happens, what we can solve is using the quadratic formula. So the reason it's so important is we can use to solve any quadratic equation. It doesn't have to be one that factors, one that intercepts. Any quadratic equation we can solve using the quadratic formula. Just like with the other ways, we always start with our quadratic equation in standard form before we solve. Alright, remember the reason things we look for standard form. First, that's equal to 0. And 2, it has that descending order, so it's very easy to pull out A, B, and C. Right, because when we factor, or we graph, or what you'll see with the quadratic formula is those A, B, and C numbers are the ones we actually use to solve. So here's the quadratic formula. X equals negative b plus or minus square root b squared minus 4ac all over 2a. So we're going to use this formula to do a couple of these example problems, and you'll see how the formula works. So here's the first one. C squared plus 5c plus 6 equals 0. This is one we saw a lot. Similar one to this when we were doing our factoring problems. Obviously, it's already in standard form. A is 1, B is 5, and C is 6. Alright, without having to look at the factors, we can solve this using the quadratic formula. So we'd set it up x equals negative b. So that would be negative 5 plus or minus square root b squared, so that's 5 again, squared, minus 4 times a is 1 times c is 6. All over 2a, and a is 1. Alright, so everything from here on out is just going to be simplifying and reducing following the order of operations. Alright, so minus 5 plus or minus. Alright, inside here we're going to square first, so 25. And we can multiply these out. Negative 4 times 1 is negative 4. Times 6 would be negative 24. And 2 times 1 is 2. So we'll keep simplifying. Negative 5 plus or minus square root 25 minus 24 would make 1 over 2. Alright, at this point we know square root of 1 is 1. So we can take that out of the equation right as 1. So negative 5 plus or minus 1 over 2. So for our final answer, what we do is we use this plus or minus to split this into two final answers. So 1 is going to be negative 5 plus 1 over 2. The other will be negative 5 minus 1 over 2. So that's how we get our two answers from this formula, the plus and the minus. So negative 5 plus 1 is negative 4 over 2, which would be negative 2. Negative 5 minus 1 would be negative 6 over 2, which would be negative 3. So those are our two answers, negative 2 and negative 3. it takes a little more work when we use this formula than factoring, when factoring works, but you can use this formula for any quadratic equation. If you spend a lot of time trying to factor one that doesn't factor, you're going to have wasted a lot of time when the quadratic formula works for all of them. So look at the second one, similar thing. We see that A here is 1, B is negative 1, and C is negative 56, already in standard form. So go ahead and plug everything into the formula. Here's one tricky thing here. B is negative, so we use negative B in the formula, it's going to come out positive, right? It's the opposite of B. Negative of negative is a positive number. So be positive 1 plus or minus square root negative 1 squared minus 4AC all over 2A. The more you practice, the more familiar and comfortable you'll be with the quadratic formula. So remembering the formula and where all the pieces go. Everything from here on out is just simplifying. Again, we're following order of operations. So we're going to square that. Negative 1 makes a positive 1. Negative 4 times 1 is negative 4. That's 56. Would be 224. And 2 times 1 is 2. Again, keep working to simplify. We're going to add those two numbers underneath the square root sign. Right, again, here you can recognize this from a calculator sheet. Square root 225 is 15. So we can keep simplifying. It's going to be 1 plus or minus 15 over 2. And again, at the end, this will split off into two answers. One will be our plus answer. 1 plus 15 over 2. That would be 16 over 2, which is 8. The other one splits off to our minus answer. 1 minus 15 over 2 will be negative 14 over 2, negative 7. So there's our two answers there, negative 7, positive 8. One thing that's very important starting out, we've been stressing this as we've been going through these, is make sure you put these equations in standard form before you start trying to solve. Alright, if I look at it right now, and I was going really quick, I wasn't paying attention, I might say A is 1, B is negative 13, and C is negative 12. Alright, but this C, that's not right, because this is not in standard form. We need to move it over here, it has to be equal to 0 to be standard form. So if we go through and put it in standard form first, we see that this C value is actually positive. Right, so we have to make sure we follow these steps, make sure we always start standard form. And then from here on out, everything will be the same as problems we've been doing. So I have negative B, since B is already negative, it's going to become positive 13 plus or minus square root 13 squared minus 4 times 1 times 12 over 2 times 1. So we plug all the A's in where the A's are, B's in where the B's are, and C's in where the C's are. 13 squared, 169. That one's on your calculator sheet. And 4 times 1 is 4 times 12 is 48. Now I've got 13 plus or minus. We subtract those two. 121. Alright, again, we look square root of 121 is 11. So we can simplify this more. simplify down there, we can split it off into our two answers. 13 plus 11 over 2 and 13 minus 11 over 2. So on top that would be 24 over 2, which is 12. Off the bottom that will be 2 over 2, which is 1. These are our two answers, 12 and 1. Alright, so you're probably noticing this is a lot more work than doing the factoring. Alright, so why are we spending all this time doing this? Well, this is why when we have problems like this up here. X squared plus 3x minus 7. Alright, if we were to try factoring this, we'd be looking for two numbers that multiply to 7 and add up to 3. Alright, there's no numbers that work. The only factors of negative 7 would be positive 1, negative 7, or negative 1, positive 7. Neither one of those together would add up to 3. So this would be one that we say does not factor. So that's why we have to use the quadratic formula. Alright, so again, using the formula, in standard form, get our A, B, and C numbers out. And go ahead and plug them in. So negative 3 plus or minus square root 3 squared is 9 plus 28 over 2. So keep working on this one. Negative 3 plus or minus square root 37 over 2. In this case, 37 is not a perfect square. There's no way we can simplify it, so here we could leave our answer just like this. Alright, it's fine to leave your answer that way if this doesn't simplify. If there's no way to simplify this. So what that leads us into is, how do we simplify? How do we know when it simplifies, and how can we simplify it? So we have to talk about simplifying radicals. So we say radicals, what that means is anything with a root sign. The root symbol is called a radical sign. Terms that have radical in them are called radical terms. So terms that are inside of, or we say underneath, the radical are called the radicand. So sometimes we'll say inside the root sign, underneath the root sign, or radicand, that all means the same thing. On some root signs, you won't see them in this class, but you take Math 2, you will see them. There will be a little number outside of the radical sign. That's called the index of the root, and it tells you what root you're taking. In this class, we're not going to see different indexes. When there's no index, it means 2. It means a square root, which is what you've been familiar with. When you see that root sign, you know that means square root. So just putting this on the picture, and this is something you'll use next semester in Math 2. This little number is called the index. It tells you what type of root you're taking. Here it's a 3, so that means we're taking the third root. And this symbol right here is what's called the radical. And this number that's underneath it is what we refer to as the radicand. So we just went to that problem, said we could not simplify that radical. So how we know when we can simplify a radical is when there are perfect square factors for a number in the radicand. Alright, even if the number is not a perfect square itself, we can still simplify it. Not always, but sometimes. And again, perfect squares, and we're going to use these in a second, are numbers that are squares of other numbers. So like 0, 1, 4, 9, 16, 25. You have the list of all those on your calculator sheets that we did on the first day. Those numbers are called perfect squares. So we're going to do one example of how we actually will go through and simplify a radical. We'll do a few examples actually. First thing we do is list all the perfect square factors. Alright, so all the perfect square factors of the number in the radicand. So if I look at 27, I know the factors would be 1 times 27, 2, nothing times 2. I can do 3 times 9, and that's going to be it. So what I'm looking for is a perfect square. And here, 9 is a perfect square. So now what I do is I rewrite the radicand using that perfect square. So instead of square root 27, I'm going to rewrite this as square root 9 times 3. And once we write this as a product, this is called the product rule, we can split the radical. Alright, the square root of a product of two numbers, so let's say it's a and b, is the same thing as a product of the square roots. So because of that, we can split this as square root 9 times square root 3. Last step is to simplify. So on this one, we know that square root 9 is equal to 3, so I can rewrite this as 3 square roots of 3. It'll be simplified. We'll do one more of these. We'll do this one right here, square root 32, simplify that. And then we have one more topic that we're covering in these notes. So again, our first step is we look at this number, we're going to list all the perfect square factors. So start, if you're not sure which one's a perfect square, just start by listing all the factors. So I can do 1 times 32, be 2 times 16, I can do 4 times 8. So here we get two perfect square factors. 4 is a perfect square. 16 is also a perfect square. So if you have two perfect square factors, you want to use the larger of the two. So here I'm going to use the 16 and the 2 instead of the 4 and the 8. So rewrite this as square root 16 times 2. Now I split that using the product rule. Remember, this up here is called the product rule. So product rule says I can split this square root, make this square root 16 times square root 2. Now I can simplify. Since square root of 16, that's a perfect square. Square root 16 is 4. I have 4 square roots of 2. So at first this might not make sense, but if you do some practice, it'll start to make sense the more problems you do. I have one more piece of notes here, and that's going to be at this part here. It's just a little warm-up to get you going when we expand expressions, when we FOIL, what these patterns look like. So this you do on your own, but we'll write this out. Remember that when we FOIL, that means we're going to be writing this out twice, so we got to make sure we hit every term. So this would be x squared plus 6x plus 9, we multiply out and combine like terms. Same thing if we multiply this one out, we'd have x squared minus 8x plus 16, and this last one we'd have x squared plus 10x plus 25. So notice on all these, when we finish expanding, we have 3 terms instead of the 2 we started with. So since these are squares of those two terms, we multiply the same thing by itself. These are called perfect square trinomials. So what we're looking for is a pattern between what we start with and the a, b, and c numbers we get in the final trinomial. So if we look at the first one, a is 1, b is 6, c is 9. And that was with x plus 3 squared. Second one we had a is 1, b is a negative 8, c is a positive 16. That's with x minus 4 squared. Last one we had a is 1, b is 10, and c is 25. And that was with x plus 5 squared. Alright, so look at how do a, b, and c relate? Well, if we look at all of these, b is twice that number in parentheses. That b number is going to be double the number we have in parentheses originally starting out. If you notice, c is actually that number squared. So using that, if we reverse the steps, we can go from one back to the other. So we know how to FOIL and multiply out and expand it. What we don't know how to do just yet is to take that and go back the other way to where we have the original two terms we started with. So what we have to do is take that pattern and undo it. So what we noticed first was that our b value was double what was in the original problem. So that means our first step here is going to be to half that number. So here, if I take half of 14, that's going to be 7. We notice the number at the end was the square. So I'm going to take the 7 and square it, and that gives me 49. Alright, the third thing I'm going to do is I want to write this as a perfect square. So I'm going to add and subtract the same number on the same side of the equation. So if I add 49 and subtract 49, I get 0. So there's no change to the equation. So I have x squared plus 14x plus 49 plus 48 minus 49. So the reason I want to write it this way is if I take these three terms right here, I notice that fits the same pattern as what we did above. So I know I can rewrite this as x plus 7 squared. And at the end I have 48 and a minus 49. When I simplify that, I have an expression that's written out as a perfect square. So since we're creating a square, this process is called completing the square. And the idea behind this is we're trying to go back from the standard form to something that you'll work with next semester called the vertex form of the equation. You'll notice in the vertex form that we always have a perfect square. So that's what we're trying to create. And we can always follow these three steps, half, square, and add. So the last one I'll do here again. First step is going to be half. So I take half of 12, and that's going to give me 6. The second step is square. I'm going to square 6, that's going to make 36. And my last step will be to add and subtract that same number on both sides. Right, I know if I do that, I'll have 0. So I have x squared plus 12x plus 36 plus 40 minus 36. Right here, we notice that fits the pattern from above. That's x plus 6 squared. And then I still have the 40 and minus 36. So I have x plus 6 squared plus 4. So it's rewritten as a perfect square, which would be what we call our vertex form. And that's something you'll get into a lot more in math too.